We have seen the EM algorithm for a specific problem. Let us now see the generic formulation of the EM algorithm. Assume that we have a dataset Dn composed of x1 until xn. We have access to the observed log likelihood of a problem, which requires to put a probabilistic parametric model on the data. We do not observe the latent variable zi that drives the behavior of the observed variable xi. In the previous example, zi was equal to delta I, standing for the Gaussian distribution to which the data belongs. If we assume that the zi are observed, the log likelihood is called the complete log likelihood and depends on the values of zi. With these notations, we can write the steps of the EM algorithm. First, you initialize the parameter theta hat 0. Then, the expectation step at the jth iteration consists in computing the function of theta and theta hat j, which is the expectation of the complete log likelihood with respect to the distribution of the latent variable z given x and the current parameter theta hat j. This is exactly what we have written before in our Gaussian example. We have computed the complete log likelihood of the problem and we have replaced the latent variable by their expected value. Since in our example the likelihood was linear in the latent variable, taking the expectation of the complete log likelihood is equivalent to replacing latent variables by their expected values. Once we have computed Q, the maximization step searches for a maximum. Then the previous steps of expectation and maximization are repeated until convergence. This is the generic formulation of the EM algorithm. The difficult step of the EM algorithm is the expectation step, because it requires to compute exactly the expectation of the complete log likelihood. This can be done for very simple problems for which data distributions are easy to integrate. There exist techniques to approximate the function Q to circumvent the problem of computing a closed-form solution for Q. Let us consider the EM algorithm described above. Can you prove that this algorithm converges? You can pause the video. We want to prove that the EM algorithm steps increase the log likelihood. First, recall that the function of interest is Q defined in equation 74, where theta prime is the parameter value at the current iteration, and theta can take any value. Decomposing the joint density p theta into a product of conditional and univariate densities, and noting that the second term is independent of z, we obtain equation 76. We let the first term be r of theta theta prime, and we note that the second term is the log likelihood. By definition of the maximization step, we want to find theta that maximizes a function q of dot and theta prime. By equation 76, one can write the difference in log likelihood between parameters theta and theta prime as equation 77. This leads to inequality 78 since the first term is positive by the maximization step. Next, focusing on the right-hand side term in 78, we have equation 79, which leads to inequality 80 because of Jensen's inequality. Since the expectation is equal to 0, we obtain that the difference of log likelihood in 77 is positive. This implies that the log likelihood increases at each iteration of the EM algorithm. You can prove with generic assumptions on the function Q that the EM algorithm converges toward a critical point of the likelihood, and with some additional assumptions on the likelihood, concavity for example, you obtain the convergence of the EM algorithm toward the maximum of the likelihood.